open questions in Piazza about the homework. So if you have any, go and put them in now. So let's just get going with the lecture. All right. Yes. All right. So the last chapter in the book is about trees, and trees are obviously very useful. There's all sorts of situations when you need to manipulate them. So you have as this example, this family tree of some people who you might have heard about or not, depending on how your interest in the British royals is. So, and I just want to introduce a bit of terminology that we use all the time. And it's basically all very straightforward. So when you talk about trees, there's one mixes a bit of biology and a bit of like family notation. So we talk about the root of the tree, and that's the thing up here. And then here you have the leaves of the tree. So they're the things here. So you'll notice that in computer science, the root is always on top and the leaves are always on the bottom. And that's because they were invented by an Australian computer scientist. So you have the root and the leaves. You then have the notation of parents and children. So we would say this one here is the parent of the node here of Beatrice, and Beatrice the child of Andrew. So you have a parent-child relationship. So every node has a bunch of child nodes. Like here, this node George has 3 child nodes. And each of these 3 children, you would say they are siblings. So 2 nodes are siblings if they have the same parent. So notice that every node has exactly 1 parent, except for the root, which has no parents. And every node has 0 or more children. And if it has 0 children, then it's a leaf. We talk about ancestors and descendants. So a parent-child are exactly 1 away from each other. So here, over here, George is the parent of Edward. There's 1 arrow away. But George the Fifth up here is the ancestor of little Savannah over here, because there is a path, a sequence of arrows that goes from here to here. The root of the tree is, of course, the ancestor of every single node. Over here, Charles would not be an ancestor of Louise because there is no path that goes from one to the other. And conversely, we say that if you have a node, its descendants are everything that can be reached from there. So, for example, the descendants of here George VI would be everything in here. And then we would call this entire thing the subtree with root George VI. So all of that terminology, I think, is completely self-explanatory. And so I have a list on the next slide. See that we covered all of those terms. So we talked about a node. Every one of those things, of those blobs here, is a node. We talked about children, leaves. Oh, interior node. An interior node is a node that is not a leaf. So, like here, this one here would be an interior node because it has children. It's a leaf is something that has no children. Parent, sibling, root, path, descendant, ancestor, subtree. Oh, height. So the last thing we need to talk about is the height. And the height is the longest path that you can make in a tree. And then you measure the number of nodes that path has. So here the longest path in this tree would go from George V to Savannah. And how many nodes do we have? 1, 2, 3, 4, 5, 6. So in this case, we would say the height is 6. Now, that's the definition of the height that we use here. I should say that some people like to define the height as not the number of nodes in the path, but it's the number of edges in the path. So those people, and you will probably get one of those people in 146, they would say that this tree has height 5. So why do I make the height this way? So if we look at this tree here, the tree that has a single node, I would say this tree has height 1. And Dr. Taylor would say it has height 0. With this tree here, I would say it has height 2, and he would say it has height 1. And so it turns out that for the formulas that we have in this course, it's a little bit easier to deal with when you count the nodes and not the edges. But I guess later on some other formulas work better the other way around. So there's no universal agreement on this. All right. So just a question to see that everyone gets this part here. Okay, here's a question for later. Okay, you're gonna have to flip back and forth here, I guess. So the tree was which one? That one that was rooted at Elizabeth II. She's here. Huh. All right, so what was height 3, 5 interior nodes, 14 leaves. Or none of the above. All right, so let's see. So we're starting here. The height is the length of the longest path, counting the nodes. So the longest path is this one here, and it has 1, 2, 3, 4. So the height of the subtree is 4. How many leaves does it have, and how many interior nodes? So these ones are leaves. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 leaves. And how many interior nodes do we have? We have 1, 2, 3, 4, 5, 6 interior nodes. So it doesn't look like any of them were true, right? So no, we have height, so it's actually height 4. I counted 6 interior nodes, and I don't remember how many leaves there was, but it wasn't 14. So that's what it would be. Let's see what the actual answer was from you guys here. And a whole bunch of people thought it had, 5 interior nodes. So let me double check if I'm wrong. 1, 2, 3, 4, 5, 6. Maybe the confusion was about the root. The root is an interior node, except in one case. If you have a tree with only one node, then that node is a leaf. But otherwise, you need to count the root. All right, tree implementation. So we have a few programs where you need to implement a general tree, and so I've put together kind of the simplest possible implementation. So, and it follows kind of what a linked list looked like. Remember, in a linked list, we have the linked list class itself that has all of the methods, and then we have a reference to the first node in the linked list. And in the tree class, we're doing it the same way. So we have this tree class that holds all of the methods, and a tree contains a reference to that first node. And within trees and nodes, more so than with linked lists, that separation is a little bit painful. As you'll see, because we're going to have to do a lot of work that also requires methods on the nodes. And so people always wonder, why do I have to have 2 classes? And the reason that you need 2 classes is the empty tree. Just like you have an empty list that sometimes is useful, you need an empty tree. So for example, we're later going to be using trees to implement sets. You might have an empty set. So in order to have an empty tree, you have to have a separate class so that you can still ask it, what's your size? You can't just use null for it, because if you ask null, what's your size, you would get a null pointer exception. So the picture is that you have the tree class. It has a pointer to the root node. That's a node. And then the node has a whole bunch of pointers to the children. That again are all nodes. So again, it's exactly analogous to what we had with the linked list. We have a linked list class that has a pointer to the initial node, and then the node had a pointer to one more node, whereas here, of course, these nodes have pointers to lots of nodes. You see those pointers here? So every node has a list of children. So in a general tree, a node can have any number of children, so it's a list. So you can think of a list actually as a very degenerate kind of tree where every node has exactly one child, except for the last one. Now, let's have a quick look at these methods here. So we have a constructor for the tree that takes whatever it is that we want to store in the root. It makes a node. It puts the data in here. So inside here we also have a data item. This might say Edward as the data item. And then each of those, would also have some data. The add subtree method gets a subtree and adds it into, I should say, it appends it past the last child. So if I were to call add subtree with some other tree t, then it would add it here after the last child of the root. And so when we look at exactly what it does is it takes the list of children of the root, it calls the add method just from the list there. There's an array list in there. And then it adds, now it doesn't add the subtree itself, it adds the root pointer of that. Let's see. So just to show how this API is used, here I'm making a bunch of trees and then I link them together with that add subtree method. And so I'm asking you to do this on a sheet of paper to sketch out the tree that you get, and to see that you get the right one, I'm asking you the question, which ones are the leaves of this tree? All right. So let's see. Starting with R, and R was Wilma. We add a subtree, and that's S. What is S? Is Dino. And then we take S and add T, which is Barney. And then we take S again and add U. So This one was R, S, G, U. So the leaves then are Barney and Fred, and that's answer 4. And that's what everyone. Okay, so looks like this is basically clear. Now, when you compute just about any property on a tree, you're going to have to do it recursively. There are very few things on a tree that can be done without recursion. So on a linked list, we always had the choice. You could do things recursively, but we didn't do it very much. What we generally did is put a pointer to one of the nodes and just follow next, or maybe previous, depending on the algorithm, to iterate through that chain of nodes. But for trees, that doesn't work because there are too many nodes. When you start at the root and now you want to look at all of the nodes in the tree, you would, let's just simulate this here. Let's say I wanted to know how many of these things start with a G. Right? And so I would say, fine, I'll look at this one first. I look at this one first. It doesn't. It starts with a G, so I increment some counter, and then I look at its first child, and it doesn't. I look at the second child. It does. So now I've found 2. I look at this one. I look at this child. I look at this child. So I found 3, and then I look at this child. But now what? Now I would have to remember how to look at the grandchildren and so on. And now how do I find the grandchildren? Now I would have to go through all of the children again and then find the grandchildren. And it gets complicated to do it like that. It's easier to say, let me recursively compute whatever, in this case, counting G's. Let me recursively do it for this tree, for this tree, for this tree, wherever that tree went, for this tree and for this tree. So for all of the child trees, so 1, 2, 3, 4, 5, 6. So on these 6 children, I will recursively get the answer, and then I just total them up, and then I take my data node into account as well. So these trees are just an intrinsically recursive data structure, and that recursion is almost always going to be a win. So generally, when you have to compute anything on a tree, you will probably want to use recursion. Now, here I have an example. I want to compute the size of the tree, just the number of nodes in the tree. That's kind of the simplest thing that you might want to know about a tree. And so, how do I compute the size of a tree? I say, well, if the tree, just the node that I'm looking at right now, that gives me 1 node, and then I'm looking at all of the children, and I'm asking, let's say if the children are C1, C2, C3, C4, then I compute the sizes recursively of C1 and of C2 and so on, and then I add 1 for the node for myself, so to speak, and I say that's the size of the entire tree. So you have this recursive formula for the size. The size of a tree is 1 plus the sum of the sizes of the subtree. So now we run into this issue that in our implementation, the tree class is not actually recursive. A tree does not have subtrees in the implementation. A tree simply has a pointer to the node. The nodes are recursive. A node has an array of nodes. And so we're going to have to write that function twice. We have to write it once for the nodes and once for the trees. It's usually easier to start writing it on the nodes because that's where it's very intuitive what you want to do. So let's look at the node function here. To compute the size of a node, what really means to compute the size of the tree to which this node is the root. Here I iterate through the children. I ask each of them, what's your size? And sum them up. And then I return 1 plus that sum. So the recursion is that here the node size asks the children, what's your size? Each child is again a node. It will be able to figure out its size because it's a smaller problem. And that's how we get our answer. Now that's the function on the level of nodes. Then we need to bring it back up to the level of trees because the nodes are an internal implementation detail so that the user of the tree can use this. And that's the function over here. And there's a special case. What if I have an empty tree? An empty tree has a root null and has no nodes, so it should return 0. And otherwise, it simply calls that function that we've just written before. So that's the general form on computing any recursive property on a tree. You make a recursive function on the node, and then you make a function, and I give them the same name because it's not really worth doing anything else. Then you need to do it on the tree class. You need to deal with the case that the tree might be empty, and otherwise you call that a recursive function. All right, let's try this with something else, with the computation of the height. So if you want to compute the height of a tree, the basic idea is to say, so here I have my root. I have a bunch of children. Each of them has a subtree. And so then I'm going to compute the heights of all of these, say h1, h2, h3, h4. And then now I don't want to add the heights, but I want to take the largest of them. So I want to take the max of them. So I take the max of all of those heights, and then I have to add 1 because the root adds 1 more length to the path. So my recursive function for the height is it's 1 plus the max of the heights of the children. So that's exactly what I'm doing here. I am computing the max, and I'm doing it one at a time. So I'm starting with 0, and then each time I ask one of the children, what's your height? And I keep an h, I keep the max of that. And so I may or may not have made a mistake in here. So let's ask this one here. It does not like me today, does it? Yeah? I'm sorry? Oh, I didn't add a 4. Thanks. Let me figure out how to edit this. Edit. Why can't I edit it? Thanks. Alright, so it looks like most people figured this out easily. So the problem here is that when the tree is empty, then the root is a null reference, and so when we now try to compute the height of an empty tree, then that gets us in here. And so then we're calling a method on what's null, and that's going to throw a null pointer exception. So that's something one always has to pay attention to when you write this function in the tree class. It needs to have that empty tree as a special case. Now, for everything else, it does work entirely correctly because it computes, here the max of the heights, it adds 1, and that's the right thing to do. So the correct answer is 4. All right. Let's try this with this one here, where I built in a different but very common mistake. So yes, this is the method of the tree class or the node class, and the answer is it's both, right? Oh, I messed up. I messed up the. Here, we need to put in a node. So what is it? Private class node. Come on. So over here, it has to be class Node. So the second one is inside the node class. So this one is the tree method, and this one here is the node method. Yeah, thanks. All right. Okay, so we have lots of people saying it doesn't work for any trees, and we have a minority of people who thinks it works correctly for some trees. So let's have a quick look here. The first thing that's we need to check out, so this is the case of the empty tree. What is the height of an empty tree? So that's kind of, I guess, a kind of a philosophical question, right? Because the height is the length of the longest path, counting the number of nodes, and so there is no path, right? But it turns out that making it 0 is kind of the best way of looking at it, and I'll show you in a minute why. So, depending on what you considered the answer for this, that was wrong. So the technical answer for this, it's definitely wrong. And the other thing is, and that's where the common mistake comes in. Look at this function. It's a recursive function on nodes. And over here we set h to 0. Then we take the max of all of these other values, and then we're returning it. And without even further looking at it, I know that this must be wrong. Because this function must return 0 for every possible tree. Right? Because there's no way of getting anything else than 0 out of it. When you take a max of a bunch of things, that takes the max of a bunch of things, that ultimately are all 0, you're going to get 0 out of it. So, and the reason for this is, and why I say it's a common error, is, the author was so absorbed in getting the recursion right that he or she didn't think about how do you need to add in the behavior of the current node. So one has to figure out that the current node does contribute 1 to the height, and now it'll be correct. And now let me explain why it's a good idea to say that an empty tree has height 0. That way, if for whatever reason you would say, this tree here has like an empty child, then that child would have height 0, and the formula would still come out correctly. On the other hand, if you had that other definition of the height, the empty tree would have height -1, which would be really strange. All right, so 2 mistakes. Wrong base case here for the empty tree, and here forgetting to take the current node into account. So like I said, the reason I'm putting these up is because they're just very common errors. And that's it? Okay, so we've seen basic general trees. We're going to look at binary trees next Tuesday. The worked example next Thursday, and keep moving on. There was a homework question. Let me get to that. So someone said, when will homework 10 come up? As soon as I have the grading stuff worked out for it. And yes, that's really not like And here the question is, how would I handle repeating numbers in the list for part A? Now, when I did this, I gave zero thought to this because I knew it would have to work itself up. What insertion sort does is I have some previously sorted part, and then here I have my part that's not yet sorted, and let's say this one here was a 4, not a 2. Then I go through these things here one at a time, and I find the insertion spot. Where's the insertion spot? Well, that's the spot where what's in there is bigger than what I currently have in my hand. So I'm looking at the 4, and then I say, okay, the 9 is surely bigger. But maybe I should have not used bigger or bigger equal. Well, in one case, the 4 would have been inserted here, and in the other case, the 4 would have been inserted here. And it doesn't matter where. So I was confident that I wouldn't have to think about this, and indeed I did. I tried out an example where there was multiple duplicates and they all got put at the right spot. Now there were several questions yesterday, I think, where people asked, do I move the data around or do I move the links around? And I still have maintained that moving the links around is the right thing. I have not seen any credible attempt where someone moved the data around. So, given that it's late in the game, don't start getting creative with moving the data around. Just move the links. And yes, it's a little tedious. And I also noticed when I implemented it yesterday that it was, I needed, I made a big thing that I needed to have the predecessor of, so here I needed to have a pair of predecessor and current so that I could do this insertion here. And later I realized I also need to keep a predecessor of this guy, because when I unlink it, I need to change this link to go like this. So I actually needed 2 predecessors. Okay, any questions or comments about this or one of the other 2 homework assignments? All right, let's move on with